Greetings, everyone. I'm Sharif with my colleague Samuel Yoga, and we shall be taking you through a few short learning for sound event detection. This presentation explores the application of few short learning in sound event detection, a paradigm that enables models to recognize and classify new sound events with very few labeled examples. So when we talk about few short learning, what do we mean? It means it's a machine learning framework in which an AI model learns to make accurate predictions by training a very smaller number of labeled data examples. So this is vis-a-vis the traditional means, which always need a large labeled data, which is always hard and expensive to get. The supervised learning, like neural networks, you always require large labeled data, which is expensive to get and hard to work with. But this one, you only focus on a few features of the data set, of the training data set that you use to make your model. It enables a model, a pre-trained model, to generalize over new categories of data using only a few labeled samples. In principle, it emulates the human ability to learn from near handful examples just from a few features and able to tell that this is this. An example which I can give is when you are taught about a species or some special bird in a zoo. So you're able to figure out the features on this species, and if this species is also brought about with many other different species, you can be able to uh, extract out a few features onto this species and be able to tell like this bird or this is the bird that was being shown at the zoo. And some of the species or the features that you can extract could be about the feathers, the color of the feathers, maybe the tail of the bird, or maybe its beak. And these are the specifics which you will be able to differentiate it from the rest. Some of the key terms involved in few short learning, we do have the support query, a small set of labeled examples used to train the model. So this will be our training data set that we are using. And on our uh, the visual that we are having, the support query is one which is in the blue background uh, on our right where we're having the dogs, the images of the dogs. So a support query would be one that is with the blue background. And then the query set, this example that that need classification. So the query set is the one that we use as our test set that we are using to test our training or our support query. Then you also have the NWE, in case short learning, we describe the classification task, where N is the number of classes. So from my example, our classes will be three, where we're having uh, that being broken down. As you can see, we have one image for the dog, then the next as you go on. Then the K is the number of examples in the class. And in our example, we are only having one on K short. And some of the advantages of few-shot learning, one, we do have efficient data utilization. Remember, the requirement for large volumes of costly labeled data is eradicated. So you can easily train from the few samples that you're having uh, using your data effectively. Then rapid model training. There is no need to retrain the model from scratch. So this saves a lot of computational power. You can use your few examples and go ahead and do it and train your model. Then we also have the cost effective, since there is less data collection and labeling that is involved, which leads to a lower operational cost and making the budget friendly. Then we also have enhanced generalization, where it improves the ability of the model to generalize from the few examples that are being given to it. Then lastly is adaptability. It can quickly adapt to new tasks other domains with minimal additional data. Then drawbacks of future planning. One, which is the main one, it is always on the data dependency. Remember, we are using a few samples to train our model. So if you're using a few samples to train our models, we need to rely on quality and high quality data to train this. Poor quality data will always lead to inaccurate results. So if you are going for this model, let your data be of quality. Then the model complexity. One, implementing future planning can require complex algorithm, and such algorithms are not straightforward like for every application. So you find that it can work maybe in sound event detection, vis-a-vis in maybe rare diagnosis in the health sector. Then also generalization issues. The model may struggle to generalize to new unseen data if the few examples are not representative of the broader set. So this is a call for everybody who is going to use this model uh, to select the features which can represent the entire data set that you're going to be using. So that in case of any maybe you're trying to predict, you can easily refer to the data set which was given. If your application, there are many, but we managed to just cut out a few one in unique handwriting recognition. It can be applied to recognize unique handwriting styles with limited samples. Then also rare disease diagnosis, such as maybe detecting cancer tumor. These are diseases which are rare. You can hardly get to know. You can hardly get their data set. This can be applied. You can apply the future planning. Then endangered species, future planning can assist on identifying and tracking these endangered species. Remember, these are species which are maybe about to extinct, so you can always use this to track them. And then here we are, now next slides, we are talking about the sound event detection, which is a task of recognizing sound events and their respective start and end time in the recording, and their respective start and end time in a recording or in an audio signal. The event detection is all about detecting the onset and offset of a sound. And the goal is to return the start time and the end time, and also the class or the label of every sound in the event or in that audio signal. We take, for instance, in the real life example where we are having, where we are having humans giving us speech, then you are having birds singing, then you're also having cars passing. So the sound event detection should be able to recognize that this speech is from a human being. Then this sound, it is a sound of a bird, a sound of bird singing, then this sound is maybe for a car passing, and so on and so forth. I remember in real life, the sound does not always occur in isolation, and it always tends to overlap each other. That's why you hear people talking, then you're also hearing birds singing, cars passing by. So all sorts of that to represent sound in the real life. And then when we talk about few shot learning for sound event detection, remember for sound event detection, you are also picking out a few samples of the event or of the sound from the audio. So for future learning application in sound detection, it becomes particularly relevant since sound event detection also focuses on identifying this and categorizing sound events within an audio. Using the previous example, we are focusing on if we are having an audio, maybe a speech from somebody, we can maybe focus on maybe the filler words that they are using. So that's just a few sample of the entire audio signal. The task that traditionally requires extensive label data sets, which we might not have, and it is also hard to get. it is expensive to make. So, and manual what the application lacks sufficient labeled samples, making few-shot learning a compelling approach to addressing this limitation. Sorry about that. Then future of the few-shot learning in sound event detection. One is improved acoustic models. So the few-shot learning will always focus on developing more sophisticated acoustic models that can learn from fewer sound samples. Then also real-time adaptation. The model should adapt to new sound events in real time. So in case it is given any sound to predict, it can always be able to identify the particular sample which is being told to predict. Then multimodal learning here involves combining audio data with other modalities such as visual for a more robust detection. The noise resilience, uh, improving the ability to detect sound events in noisy and complex acoustic environment, which we are always in the real life example. Take for instance, Kampala downtown. So in case this model is being used in Kampala downtown, can it be able to detect that this noise or this sound is for a siren and something similar to that? And then I'll also talk about the sound event detection pipeline with few short learning. The first stage is data pre-processing. Data pre-processing involves preparing this audio signal before being taken to the training model. So we do convert this audio into meaningful representation, such as spectrograms, male frequency, or the planning embeddings. Then at this, then after we do normalization, where we have to ensure that uniform amplitude levels to enhance motor robustness, and also we do what we call noise reduction. So we are trying to clean our data. So reduce on the background noise. This will improve the feature clarity and prevent misclassification. So you can easily tell that this is this sound will be for the siren or for just a vehicle that is passing by. Then the second one is model training. In model training, one, we do have the support and the query set. So we divide the available labeled data into training and test subset to simulate the real world example. So that the training set will be the support test. So it will be the support set. Then the test set will be the query set. So we do use this to try to come up with our model so that it can be able to also be applied in the real world. Then the other, utilizing metric-based model. This one involves using different frameworks for the future planning, which can be applied for sound detection. Then lastly is inference, where we are classifying, where we are taking this sound, this model to the real world. So it involves extracting features from the query sound clip. Then we try to compare from our land representation in the training model from the support set. Then after that, we do classify the labels based on the similarities uh, of the spores. Is this then? Is this maybe is the sound? Is it similar to this and this category? That's what it's all about in the classifications, uh, in the classification phase or the inference stage. Yes, please. That's all from me. I'll hand over to my colleague to take you through the next part. Thank you.
Thank you very much, Mr. Sharif. My name is Samuel Derrick, and I'll be taking you through the various approaches to future learning for sound event detection. Future learning enables models to generalize from a limited number of labeled sound event samples, and various paradigms in future learning can be adapted to sound event. And we have three main approaches, which are model, metric, and optimization based approaches. So to begin with, um, model-based approaches we have the MANs, which are short for memory augmented neural networks. So these are memory augmented neural networks. There are various models which use external storage to facilitate the learning. They have the neural Turing machines, which have the controllers, which are mainly designated to read and write to memory. We ensure that memory can be encoded and the captured information of new tasks. In the meantime, we ensure that previously stored representations can be able to be accessed in a stable manner. Thus, to ensure that these continuously evolving sound environments, such as smart home monitoring systems and the wildlife acoustic analysis, are able to adapt to these super fast changing sounds in their environments. Thus, this approach is particularly useful in dynamic environments. Then next we have the meta networks. So in meta networks, we want the model to adjust from a few data set without explicitly training it with another data set. So instead of training a new model from scratch, each new sound event, meta networks learn a meta model that can generate task-specific parameters in real time. And they combine fast weight layers and slow weight layers to make predictions in these neural networks. Thus, this approach is significantly reduces the need for large label datasets and enables models to generalize to new sound events with minimal fine tuning. Then next is the metric-based approaches, where we have the prototypical networks. These now the prototypical networks, they categorize various sets into prototypes, which use a minimum. They use a mini feature embedding. They are mainly in two categories, that is few short and zero short, whereby in few short, uh, as you can see in our picture, we have three classes, C1, C3, and C2. So these classes represent each prototype. And when a new event X is classified basing on its proximity to the nearest prototype. And here the model has seen a few examples. For example, there's those small circles around each category. Those green ones for the C1, the blue ones for C3, and the orange one for C2. So thus from each class, this helps the model to generalize this unseen instance of the sound type. While in this zero short classification, here, unlike few short, the model encounters a completely new class. That is, for instance, C2 and C3, they have they have never trained on anything on this sound. Instead of relying on a support set, we use the semantic vectors, that is the V1s and V3 and V2. The new sound event X is mapped to the closest conceptual representation using a similarity matrix, even if it has never been explicitly trained on that class. Uh, Next is the Siamese networks. This use similarity functions between pairs of sound samples, and they are mainly applied where in situations where we want to categorize highly similar sound events, such as let's say a barking dog and a howling wolf, they almost have the same sound. So you can use these Siamese networks to categorize each of them. For instance, if you have this wolf down and the dog up, and then we come up with a dense layer with the sigmoid activation, similarity of I1 and I2, we get the loss calculation, and then we compare it with our target sound. So that's how CMAs work, just like the conjoined twins in humanity, whereby they share everything. They are almost similar. Next is mm, the consign similarity based methods. So consign similarity here we are mainly considered concerned with the angular similarity between the two sets. For instance, in our image we have hi world and hello world. So we calculate their angle between. In cosine similarity, we use we categorize the various sounds in terms of features, and we calculate that the angle between them using the cosine rule. So if theta is more or less or equal to 1, that means that the two sounds are similar. If it is closer to 0, then those sounds are different. In our daily example, we could say something like if, for instance, if a barking dog and a howling wolf, if they produce the same sound in our cosine similarity, we categorize them as similar. But if we say maybe the sound of, let's say, a car horn and a whistle, those are two different sounds. So using cosine similarity, their angle will be kind of very different from each other. The angle theta will be closer to 0. Uh, then we have the optimization based approaches. Uh, these use gradient descents. For instance, we have the MAMO, which is the model agonistic meta learning. Here, for instance, we are feeding our model with different sounds from a bird, a dog, and a frog. So this model comes up with its initial classifier. Here we are separating into the tray. We are separating these sounds into training sets. Now, if a new sound which wasn't actually classified before is introduced, this model is able to do the classification scores by getting those sounds it initially used from its initial classifier to come up with the end classification of that sound. Thus, this method is particularly effective in real-world audio environments where new sound events emerge frequently and large level data sets are unavailable. The next is the reptile. Reptile is more like the mammal, but the only difference is that reptiles moves the model weights towards the new parameters. So reptile works in a more in a way that sorry, excuse me. In reptile, we get a sample and we train that sample. Then after training that sample, the we, we, for instance, theta 1, theta 2, theta 3, and 5, 6, those are the various samples the model keeps on training. And then it moves the model weights towards the new parameter. So each time we train theta 1, after we are going to move its model weight theta 2. And this method is computationally efficient and well suited for low resource environments, such as those embedded audio recognition systems and the wearable devices, which usually detect ambient sounds. Then the applications of few-shot learning in ESD have smart homes where we are able to detect the difference between a closing door, crying baby, breaking glass, then healthcare, whereby we want to detect the different patterns of a cough. For instance, this was used during the COVID days where different cough pitches were used to determine that this person is really badly off, and then to monitor elderly individuals through their sound cues for fall detections. And then they are also applied in wildlife monitoring to identify rare animal vocalizations for ecological researches, they detect poaching activities by analyzing environmental sound signatures. Then in industries, we use SEDs to detect if a machine is still functioning well or whether it has become faulty. For example, a printer, usually new printers do not make sounds, but if a printer starts making those squeaking sounds, then you can come to a conclusion that it has become faulty by leveraging this few-shot learning in SED. Then the main challenges we usually face when you're training models, that is the limited level data where many sound events lack sufficient annotated samples, and then the background noises, that is ambient noise which can degrade the classification accuracy. Usually, for instance, if you're applying SED in traffic, for example, in a car, which will detect maybe alarms, and then the cars are beeping all the way. It may not be able to detect an ambulance alarm. Then the generalization issues, usually models may struggle to adapt to new environments with unseen sound patterns. For example, a model which was trained in a city may not fairly be able to adapt in a village. Then, so the solutions, we do what we call data augmentation, where we apply transformations like bit shifting, time stretching, and synthetic data generations. Then, self-supervised learning, we train models to extract useful information from unlabeled data. This makes the classification a bit easier because they usually do the correlations and the similarities to come up with the useful information. And then the domain adaptation, I transfer knowledge from one costing setting to another to improve robustness. Then we have the evaluation metrics for SED. So various models have various evaluation metrics, but usually we have the gen evaluation metrics. So mainly the ones we use, we have accuracy, precision, recall, F1 scores, and AUC with ROC. Whereby accuracy, we are mainly studying the proportion of correctly classified sound events. And then we have the precision, which is usually a fraction of the corrected classified positive sound events. And the recall, which is the proportion of actual positive sound events which are correctly classified. This is mainly seen, these parameters are part of what we call usually the error matrix, which we sometimes use. And then we have the few-shot learning performance metrics that are the sample efficiency, if the model is able to assess performance given the limited data. And then can it adapt to quickly to model generalizations to new sounds versus with minimal training? Yeah. Then the tools and frameworks, you have PyTorch, TensorFlow, and then Learn to Learn. Uh, PyTorch, which is a flexible deep learning framework widely used for FSL. And then TensorFlow provides scalable machine learning solutions. And then Learn to Learn, which is a specialized library for meta-learning applications. Then the audio processing libraries, we have the browser, which we use to extract features from audio, such as spectrograms, chromograms, and then the Torch Audio, it integrates with the PyTorch for sound processing, and then OpenL3, which is a deep learning embedding for robust sound classifications. These are just a few of the models, but various libraries we can use and tools. Then the future research areas, we have zero shot. So here we shall mainly we want to enable these models to classify sounds events without prior labeled data. That is, we have seen it in prototypical models, whereby a model will be able to classify any sound without having prior knowledge of it. And then cross-domain few-shot learning, where we're enhancing model adaptability across different sound environments. And then multimodal feature learning, we are integrating audio with other modularities such as visual, textual data for improved classification. So these may include spectrograms and chromograms to be able to account for various phonitions and other features. Then emerging applications of these SEDs, we have edge computing, where we're deploying SED on lower power devices for real-time processing. For instance, we put them in industries and maybe simple offices to detect the different various noises, sounds produced by the different gadgets such as computers, printers, and then autonomous vehicles. For example, those Tesla vehicles which can detect an ambulance and drift off the road to give it away. Then you have the smart wearables. These are the fitness trackers, those simple watches we usually put on. So I think that will be all. Thank you very much. I mean, as somebody with Yoga, thank you very much.